Swayam Prabha. Digital India. Educated India.
What is a good plan is, I know I have given this as a homework, but I am going to just do this now. Okay, we will just do this here in class. We can assign something else for the homework. Yeah, this is basically a DC motor model. Yeah, and what I had asked of in the homework was to basically verify the two lemmas, point 1 and point 2. So what I am going to do is basically try to just, let's see if we can do this on our own, and if we remember all the ingredients of this lemmas, right. So that's basically what I wanted you to verify. I think that's quite visible. Yeah. So you see that there is some nonlinearity here and here. Let's not worry about what the parameters are and so on, what theta is, what AB is and so on. That's not our concern right now. We just want to verify these lemmas. Okay. And we are also given an output with which respect to which we want to work. Now, the first thing is, what was lemma 0.2? Sorry, 0.1. We are just verifying that all this, if you are given that LGH equal to LG LFH all the way to LG LF R minus 2 H is 0, then you get that L, yeah, I am just going to copy this, I guess. Then you can basically claim that all the L add F K's are also 0. Okay. Yeah. So you can claim that L add F K G H is 0 for K equal to I guess 0 to R minus 2. Okay. Because I am just specialized it to relative degree R. Okay. So the first thing we want to do obviously is to compute these. Yeah. Let's start computing. So first things first, what is F? What is the drift vector field? What is the second term? Handwriting is very nice. I think this is also a controller. Wow, wait a second. Bx2 plus ua, no, that's some k. Yeah, it looks like it's just some constant. Okay, this is just k. Yeah, good handwriting. All right. All right, fine. What is f? Let's start. Minus ax1. Okay. Second component. Yeah, the whole thing, right? Third component. Excellent. Everything without the control. And G is excellent. Yeah, great. Okay. What is h of x? Is x3. Yeah. Of course, one simple way to do your find relative degree is to start taking derivatives directly and find relative degree. But unfortunately, I have asked you to verify the lemmas. Yeah, or ask myself, I guess, in this case, to verify the lemmas. So we'll actually have to compute all this. All right. So if you see that the first term here is also LGH, right? Because if I put k equal to 0, this is just LGH, right? So let's just compute LGH first. What is LGH? First I take partial of h with respect to x. What is it? Partial h with respect to x? 0, 0, 1. Thank you. And g is just 1 0 0, so obviously 0, done. First done. Let's do LG LFH. Did I get this correct? Yeah, I think I got this correct, right? What is LFH first? LFH is again 0 0 1 multiplied by this mess, minus AX1 minus BX2 plus K minus CX1 X3 theta X1 X2. Okay, what is this? Theta X1 X2. Thank you. Alright, now we do LG of LFH. Or LG LF, I can put the bracket, that's fine. Yeah, it's a distributive operation. Now if you want to do LG of LFH, what do I have to do? I have to take partial of this guy, right? What is it with respect to x? Yes, go for it. Theta x2, theta x1, 0. Now, and I multiply with g. Now did I get something? Thank God, I got something. Yeah, this is what? Theta x2, right? Okay, done. What was relative degree? Relative degree is what now? R minus, so this has to be 0 until R minus 2, right? So it was 0 until k equal to, it was 0 until what? 1. Relative degree is 2. How did I get 2? From this expression, how did I get to 2? I got that only LGH is 0. So this term has to be LGH. So R minus 2 equal to 0. So R equal to 2. Great. Just okay, just the last term has to be 0, right? Alright. So then I have to of course do this also. I have to prove that I have to now compute L add F 0 GH also, but this is actually equal to what? L GH, which is already proven to be 0. So proving, so lemma 0.1 proved. Yeah, too easy because I didn't have to compute any further derivatives at all. Done. Okay, great. What was lemma 0.2? It was the linear independence. Alright, linear independence of DH, DLFH and so on and so forth. Okay, in this case how far do I have to go? Only till R minus 1. So what is R minus 1 in our case? 1. So I just have to go till LFH, LF1H whatever, or LFH. Yeah. So this is, that's it. So I just have to compute this much. DH and DLFH. What is H? Sorry, what is DH? We've already done this. It's 0 0 1. What is DLFH? Did I get this right? Yeah. DH is correct. LFH is this guy. What is the D of that? We've already computed that also. Yeah. Theta x2, theta x1, 0. Okay. This is linearly independent, right? I mean, okay, let's be precise, right? If you remember, we always talked about this linear independence for a particular point. We said at x0. In this case, this is rank 2 for all x1, x2 not equal to 0, 0. Okay, x3 can be anything. Notice, x3 can be anything, it's irrelevant, but x1, x2 both cannot be 0. Okay, and of course you can assume theta is not 0, otherwise stupid system. Yeah, alright. So both x1, x2 cannot be simultaneously 0. Okay. x3 anything is allowed. Okay, then this is rank 2. We are done, we have coordinates, right? So what are our coordinates now? y1 is hx itself, which is x3, y2 is lfhx, right? That's what we chose, which is what? Theta x1, x2. Yeah, that's it, I think, right? We only get 2 coordinates, right? Because I mean, how many do we get? Until r minus 1. right? We get until r minus 1. R minus 1 is just 1 in our case. So we get h and LFH. These are the two coordinates we get. Now what is the third coordinate? I don't know. I don't know what I can choose. I just want to make the whole thing a diffeomorphism. Alright. So as of now, what did I get as the Jacobian? I got it as 0, 0, 1, theta x2, theta x1, 0. Yeah. Now what should I choose as my third coordinate? Any guesses? Basically I need it to be linearly independent from y1 and y2. That is, in the Jacobian it should contribute a third dimension. What do you think? I think something like minus x1 and x2 0. This will work, right? Because that makes these orthogonal. नहीं क्या उल्टा कर दिया नहीं ना this makes it orthogonal, right? I mean just dot product of the dot product of these is 0, right? That's, I just use that idea. So if this is the Jacobian, then I'm good, because this will be rank 3. Because if you notice, if you take the determinant, this is always okay, no problem. Yeah, always going to give me one independent row or column. The determinant of this is what? Theta x1 square plus x2 square, right? So if it's not at the origin, it's okay. That's the best I can do. So so I can take this. So what will be the y3 such that this is the Jacobian? Partial with respect to x1 is x1, partial with respect to x2 is x2. Half x1 square plus half x2 square. Yeah. Alright. So I sort of back calculated this. Yeah. No point adding anything here. I see, this is the trick. I'm just playing a trick here, right? I'm just adding a state so that I get this diffeomorphism. No, that's all my aim is. So adding anything here is pointless, because already have full rank in this. No problem. No point adding anything here. How to make these two linearly independent? Make them orthogonal. The best way to make any two vectors linearly independent is make them orthogonal. This is the best way to do it. So I just do x1 square by 2 and x2 square by 2. Very, look at this, very crazy looking coordinates I got, right? Unusual. Started with very nice looking output, yeah, but then I ended up with almost looks like my Lyapunov function, right? I got almost a Lyapunov candidate in the first two states, right? But whatever, this is a fair set of new coordinates. Okay. Now what will happen? I mean, if I actually write the dynamics, yeah. हाँ क्या मिस किया है कहीं तो माइनस है ना सब. You guys always wait till the end to tell me which one is minus. This one. This one, no? Thank you. Alright, so not a Lyapunov function. Excellent. I like that. Alright. Whatever. Right. Yeah, funny system. I mean, I wonder that can it be simpler? It could be, but then what will happen is I could try something simpler. What will happen? That do is it will restrict the x1, x2 in which this will work. Right now it will works for a very good class of x1, x2. Basically, whenever both of them are non-zero, it works, right? Which is what was the assumption here also. So this works whenever both of them are non-zero. Sorry, any of them is non-zero, not both of them. Any of them is non-zero, this works, right? That's pretty good, right? Because usually I always want to drive my systems to 0. So it works all the way till the end. Then it doesn't work, it doesn't work. I mean, you can see that I work almost till the end, right? If I choose something simpler, I think it will become restrictive if I tried anything else. If I remove this, for example, if I remove this guy, if I made this 0, what would that do? Determinant will be theta x2 squared, right? So x2 will have to be non-zero for this to work, right? So yeah, I mean, you can think of other fun choices, but yeah. Let's try to compute the dynamics in this new variables. Let's see what I get. Y1 dot is what? X3 dot. X3 dot was what? Theta x1, x2. Oh, that was expected, no? Y1 dot was supposed to be y2. Sorry, that is the whole point of this whole exercise. Yeah, y1 dot is y2. Yeah, what is y2 dot? Y2 dot is the derivative of theta x1 x2. So that is theta x1 dot, which is ax1 plus u minus ax1 plus u times x2 plus theta x1 x2 dot, which is whatever minus bx2 plus k plus cx1 x3, right? Something funny. The only thing is my control appears here. Only thing is the control appears here. Again, it's very difficult to actually write this in terms of the y1, y2 and y3, so I am not even going to try to attempt this. But the control appears here, that is the good thing. Yeah, and then if I do y3 dot, I get half x1 square half x2 square, so the derivative is minus x1 dot, which is minus ax1 plus u plus x2 dot, which is x2 minus bx3 plus k minus x1 x3. Okay. So again, if you see, the control appears here also. So the control appears now in two equations. Okay. Could have been avoided again if I got rid of this guy and got rid of this guy. Control would not appear here. Then you would have control only one equation. May have made control design easier. So this now then the choosing the third coordinate really depends on a lot of factors. Of course, you are trying to make it a diffeomorphism, but there are infinitely many choices, right? Then it is really on what's good for you. Okay. So I think I don't know, did I try to, yeah, I did something interesting here. If you see, I chose this. Yeah, if you see the previous page, z1 was x3, I used the notation z1, z2. Z1 was x3, of course, z2 is theta x1, x2. These we have no choice, this is what it is, right? Z3 I took as x2 minus k over b. Okay. Now, why did I do that? Then because I got z1 dot is z2, z2 dot is whatever, and z3 dot is this nice expression. I have no idea why I chose this, but if I take z3 as what I chose, x2 minus k by b, then what happens, look at this, what happens. If I choose z3 as x2 minus k over b, right, then this guy, the third row becomes what? The derivative, right? It's just the partial of this, so it will be 0, 1, 0, right? Because this k by b is some constant, right? This is also not a bad choice actually, if you think about it, right? Because it gave me a good extra column, right? And then this is what it is. If one of them is, any one of them is non-zero, I am fine. So actually this was a simpler choice, right? Because this is just actually linear, right? Any linear transformation is always nice, right? From a starting from one coordinate, you move to another coordinate in a linear way. This is also a nice choice because it gave me a nice full, these two are already linearly independent, depends on nothing, okay? And then this one, all you need is, well, actually in this case also, no, it is not that nice. In this case also you must have x2 to be non-zero. I apologize, it is not that nice, by the way. Yeah, sorry. You will need x2 to be non-zero, because if x2 is 0, then this goes away. You could have something here, but then this becomes the same. Yeah. So this will also need x2 non-zero. Yeah, whereas this choice, even though it is ugly looking, only x1 square plus x2 square non-zero is required. Okay, all right. So this is how you work with feedback linearization. Eventually, all those complicated looking expressions, you only use some part of it. In this case, you only used r equal to 2, right? So those expressions are significantly less in number, but the computations are exactly like this. You have to do this partials and multiply and so on and so forth. Okay, all right. Any questions?
Does R have a physical meaning? What if R was equal to n,
then you will have full state feedback linearization, which is what we will see next. In that case, the system is completely linearizable. Yeah. Physical meaning, yeah, I mean it has physical meaning in the sense that it connects how your output and input are sort of, you know, again if you are looking in terms of whatever is your R, your system has a subsystem which is an R dimensional transfer function. Basically it has a larger system with additional state, but then in the middle there is sitting this R dimensional linear system. So it's almost like saying there is, yeah, I mean then there's these notions of, I mean anyway I unfortunately will not have time to talk about those, but there's this notion of differential flatness also, if some of you have seen this. Basically it says that, yeah, you take a certain number of flat outputs and all the system states and the inputs can be represented as these flat outputs are their derivatives, right. So again this is also a similar notion, right, there you are, it's a property of the input output system, yeah, it's somehow making some part of the system linear, so the behavior will be linear, yeah, whatever all the robot dynamics cases, I mean it's fully feedback linearizable, right. So it actually behaves like a double integral, it behaves like a linear system, yeah, particularly easy to control, particularly easy to work with. Other than that, no, I don't know of any other physical relevance. And controls folks attach physical relevance to sensors and actuators, right. So if there is a linear connection between the sensor and actuator, we really love it, right. So we can do so much, yeah, we can even, you know, most importantly, why? Because we can get performance, right, we can talk performance, transients. Non-linear systems, yeah, now there is so much literature on transients, but linear systems, it's so mature, right, how much overshoot, how much, you know, damping, you know, how will the oscillations look, these are also like critical values, critical. Yeah. So that's the physical relevance for us, alright, yeah. Fundamentally there are robustness issues with feedback linearization, it's not Lyapunov based, as you can see you are cancelling things, we will keep trying to cancel things, yeah. Even this dynamics we saw in the end, if you see, you got this structure, right, a rather complicated looking structure here, you got the control here and you got the control here. Notice you had ux2 and minus ux1, you see this orthogonality sort of in the control. You remember in a Lyapunov function things, you would just take it as, you know, if you take x1 square plus x2 square, it sort of cancels the 2 in some sense, okay. But you have ux2 theta and minus ux1, of course you can have a theta, it does not matter. You will see that we are not asking for x1 and x2 individually to be non-zero, but one of them to be non-zero at least. So if one of them is non-zero, say x2 is non-zero, yeah, and this is 0, then you cannot do anything with this state anyway, but this state you can make this whole thing linear by cancelling all the non-linearities, right. So because it is a relative degree 2 system, you can only get a 2-dimensional linear system. Similarly, if x1 is non-zero, then this system can be made linear, this still remains whatever it is, okay. So you again get a 2-dimensional system which is linear, that is the whole idea, alright, okay. Any further questions? Alright, we will stop here.